All right. Next talk in the session will be on how to compute call graphs for the Android implementation of WhatsApp. It'll be given by Ecos.
Cool, yeah. Thank you for the intro. I'm Ákos. I work at WhatsApp, and today I'm going to give a talk on how we use the call graph reachability analysis in order to improve the health and the performance of the Android app. So this work pretty much started with a request from the Android app health team, who came to us and asked, can we find instances where certain performance critical functions end up potentially transitively calling computationally expensive functions? Like, for example, they are doing something on the UI which checks something and then it reads from some database which is potentially slow. They wanted to flag these kind of cases. And we said, yeah, probably we can do something about it. For this, we need two main things. One is the specification. So we need to know what is exactly performance critical and what is computationally expensive. And then we need an analyzer which is automated and fast enough to give feedback on code changes at the scale of WhatsApp. So in theory, this is a relatively well-known and well-studied problem. It's called reachability analysis, where you have a set of sources, a set of sinks, potentially some sanitizers as well, and you want to check whether there is control flow from source to sink without going through any sanitizer. This is slightly different from some of the previous talks today, where they were about taint analysis, where you're mostly interested in tracking data. Here we are mostly interested in tracking the control flow, but one common point is that we also employ call graphs, and in particular, an approximate solution is to use the static call graph. In one of the previous talks, there was a lot of discussion about the different precision of call graphs. In general, this method can work with any kind of call graph. For now, in the current implementation, we use a very basic static call graph, which is based on the static types of the program. So basically, if you have something like this, where you have some sources, you have some sinks, you have some sanitizers, then, for example, this path on the red is something that you would want to report and flag. But for example, this blue one is fine because it goes through a sanitizer. Now, how do we do this in practice? So we turn to our in-house static analysis platform, Infer. It's developed at Meta. It has been running for more than 10 years, finding thousands of bugs every month at a large scale. And Infer supports multiple languages, including Java and Kotlin, which is great because that's what WhatsApp Android is primarily written in. And it also has a bunch of checkers related to all sorts of properties, including memory safety, data races, deadlocks, temporal properties. But it also had a checker which was called annotation reachability. So it was a very good candidate to look at. And as its name suggests, in annotation reachability, the specification can be done using Java annotations. So for example, I can mark my performance critical and expensive functions in the code using Java annotations. And then in the configuration file of Infer, I could say like performance critical is my source, expensive is my sink. So that's how we can specify these functions. And how do Infer checkers work? Well, Infer checkers are modular. They analyze one procedure at a time independently. They mostly use abstract interpretation, so they propagate some abstract state in an abstract domain through the function or procedure in order to obtain a summary. And it's compositional, which means that this summary that we obtained can be used in different calling contexts. So if there's a function which is being called in different contexts, we don't need to analyze it multiple times. We can substitute this summary in every calling context. And it's on demand, which means that dependencies are analyzed as needed. This will be interesting when when we see recursion, but I will get back to that later. So for example, if we have some function foo that we want to analyze, but it calls function bar, then we first analyze bar, come up with a summary, put it in our database so that we can reuse that to compute the summary of foo. So this is how infer checkers work typically. And for annotation reachability, I will first go through an example. So we have this example from before, and here you can see the dependency between the functions. So first, infer would analyze read from database, which from the perspective of this checker, it doesn't do anything because it doesn't call any function, so it will just provide an empty summary. Then we go to check something where we see that in line 7, it calls this read from database function, which is actually a sink annotated with expensive, so we put this in our summary. And then when we go to something on the UI, we see that we call check something in line 3, which itself is not a sink, but there is a sink reachable from it, namely read from database, which is expensive, so we put this information in our summary. And finally, what we see is we have a function, something on the UI, which is marked as a source, performance critical, but its summary says that it calls something which is expensive. So this is something that we would report as an issue. And we can also reconstruct the path by traversing these summaries in the other direction. So just to formalize this a little bit, in the abstract domain of this annotation reachability checker, the abstract state of a function f is a set of these GNHE tuples, which basically mean that in the current function that we're analyzing, f, at line n, we call a function g, which eventually reaches some function h, which is annotated as a sink with the annotation a. So basically, in every summary, we are storing just single steps towards the sink. And initially, we start with the empty state. We traverse the instructions of the function in order. And the way the transfer function works is that if we see some call to some function g, then we check if g itself is a sink. Then we add an entry that we directly call a sink. But if it's not a sink, then we check whether it can reach any sink. And if yes, then we add like a so-called indirect entry. And we also check for sanitizers as well. And interestingly, the join operation is simple set join, and the summary is the state at the exit of the procedure. So this means that this is both flow and path insensitive, which means that in some sense it's over-approximate because, for example, we would report calls that are guarded by infeasible conditions, but it's also under-approximate, for example, if there is a dynamic dispatch or lambdas involved. But in our context, what was really important is to be scalable and to find meaningful bugs with a relatively low false positive ratio. So we are fine with making these trade-offs. And now this checker was mostly working well for our purposes, but we did have to make a few extensions. One of them is to support the specification of function via regular expressions, primarily because we had external code that we wanted to annotate, and we can't really go in and modify the source code. But it also allows us to express our properties in a more compact way. For example, in one of the properties, they wanted to say that every UI event handler is a source. So basically, you could just say that if it matches some regular expression over some base UI class, then every derived function should be treated as a source. But this also opened up the opportunity to support other languages which doesn't have annotations. And another thing that we did is minimization. So in general, nothing prevents a source from calling another source or a sink calling another sink. So we came up with these concepts of paths being source and sink minimal, with the idea being that, for example, here if you somehow eliminate or you break the chain in the middle, then you solve all the extended issues as well. Now, how does this, so what did we do in practice for WhatsApp Android? Basically, we collaborated with the app health team, and we came up with 2 properties, which together use 8 annotation and 11 regular expressions. In the first property, the sources are performance critical functions, typically things that happen on the UI, so UI event handlers, and sinks are computationally expensive functions, worker threads or file I/O operations. And we also had some sanitizers. These are typically features that are not shipped in production builds. So for example, tests or debug utils or like these Java precondition checks. And there was another property as well, where the sources and the sinks were based on threading annotations that are incompatible. So I think it was the source is worker thread and the sink is main thread annotated function. Those should not be called directly, so that was another property. And to break it down a little bit, you can see the 2 properties, and you can see how many source, sink, and sanitizer annotations we used, how many regular expressions we used, and we also have some data on the coverage in terms of all the procedures or functions that you have in WhatsApp Android codebase. I put these relative numbers because of confidentiality, but the key point here is that WhatsApp Android has multiple hundreds of thousands of functions. So even if you see percentages like 1 or 0.2%, that is still multiple hundreds or multiple thousands of functions. So this is like a non-trivial number of sources and sinks to be analyzed. And for the second property, we have a higher number because that reused more of the existing threading annotations that were already there in the code, whereas for the other, the first property, these annotations were mostly put in the code just for the purpose of this particular check. And so the way software development and static analysis typically works at Meta and WhatsApp is that we have the developers who submit code changes. At Meta, we call these diffs. You can think of it as a lightweight pull request. Basically, every commit needs to go through a review process. So it's like a unit of code change. And here we have the human reviewers who can accept the change or write comments. And at the same time, we also have CI running with tests, static analysis, and all sorts of checks. And this is where, for example, Infer would report this bug. So if you would submit this example, then Infer would tell you that you have this problem with performance critical calling the expensive function. And then we also have a trace. Infer would show you how exactly you end up going from the source to the sink, which was very important because in production, a lot of the examples that we saw had often traces of length of more than 20. So this was very helpful for developers, and they could click them through in an interactive way. And once the reviewer comments come in and also the signal from static analysis, then the diff goes back to the code change goes back to the author, so they can submit a new version. And let's assume that they fix, all the problems flagged by static analysis, all the problems flagged by the reviewers. Then after some point, the code gets merged into the main branch, and we still have a continuous CI running periodically on the latest revision. And if it finds any problems, then we have the option to file tasks either fully automatically, manually, or in a semi-automated way, and assign them to the developers. Why is this needed if we already have the analysis during code change time? Well, sometimes developers ignore the signal, so bugs can slip through. Also, on code changes, we want to be much faster to give fast signal to developers. So typically the analysis that we are doing is more shallow, whereas in these continuous periodic runs, we have much more time, much more resources, so we can do deeper analysis. And it is also possible that you have two code changes which are individually fine, but then once they get merged, they have the bug. So this is also another line of defense. And the way we deployed it is first we checked with the periodic runs. We wanted to see how many pre-existing issues there are there in the code base, what's the quality of the reports, and what's the volume, because if we have too many issues, then developers would simply just not care. And we found that without any minimization, we have 12,000 issues, and after fixing a few obvious false positives, the signal quality was actually quite good. These were mostly true positives. However, it was still too large, like, okay, which ones do you fix, like where to focus? So we applied source and sink minimization, and we found that sink minimization already reduces the number of issues by an order of magnitude, and this is actually quite a manageable level. So we decided that source minimization is not needed. And in addition, usually the sources are closer to the actual business logic, whereas sinks are often down in low-level libraries or utilities. And in general, developers are much more comfortable fixing code that is closer to the business logic or closer to the code that they own. And so after we were happy with the quality, then we started to roll out this on every code change, first in a so-called shadow mode, where the analysis was already running for every code change, but the developers did not see any signal. It was only us who saw the signal on some internal dashboards, so we could see exactly what would the tool report on which code change. Then we had a group of early adopters, and then we had the full rollout. And so to give some results, in terms of the pre-existing issues, we filed around 60 tasks in a semi-automated way. And so far, in the first 3 months, I think, up until the paper was written, 7 have been fixed, which is not a huge number. In general, this was sometime in the beginning of the year, so that's not really the season where people fix pre-existing problems. However, some of them we could relate to actual production data, and there was one particular example which was related to crashes happening in production. ANR is app not responding. I think it's when the app doesn't respond for like 5 seconds and the operating system kills it. So there was this example which could directly be linked to these production ANRs. I think what happened there is there was some eligibility check for a feature that was only enabled in certain regions, and this was running on the UI thread. So on the one hand, it was not necessarily to do for every WhatsApp user, and on the other hand, even for those users who were in those regions, this should not be done on the UI thread. And so the engineers seen the issue, they fixed the problem, and then they did a controlled experiment where the fix was already rolled out to some users, and it was not rolled out to the other set of users, and the number of app not responding crashes were reduced by 0.5%, which again doesn't seem like a huge number, but considering that WhatsApp has more than 2 billion users, this is actually quite a big number. And it also made chat loading speed up. It also made chat loading for everyone 1.25% faster, which again, at a scale of WhatsApp is actually a considerable win. And as I said, we also rolled this analysis out for code changes. And in the first 3 months, Infer has reported around 170 problems, out of which 90 were fixed. So it's like the fix rate is slightly above 53%, which is quite typical for the static analysis that we are doing it in Meta or WhatsApp with the other kind of issues. So we were also quite happy about it. We did look at some of the unfixed issues to see what's happening there, and we found quite a few interesting categories. One was related to Kotlin conversion. So when you convert a module from Java to Kotlin, then basically Infer would report this as so you move the pre-existing issues and Infer would report this as new. Infer does have some heuristics to match issues, like for example, if lines are shifting, then it wouldn't report the same issue as being new, but converting to a new, like a different language was beyond the scope of these heuristics. Another interesting case was related to mutual recursion and scheduling. So as I mentioned, Infer has this modular analysis where it needs to analyze dependencies first. Now, what happens if there's a mutual recursion? Well, you can either do a fixed point computation, but Infer doesn't do that. It just simply unrolls to a depth of 1, which essentially means that it cuts the dependency graph until it becomes acyclic. And so what happens here, for example, in this example, is if you cut the edge from G to F, then you would see the issue. But if you cut it from F to G, then there is no path from source to sink, so you don't see the issue. And the scheduling in Infer can sometimes be non-deterministic, especially if the code changes. So what happened is that on every code change, Infer is run twice, one on the parent revision and one on the current revision to compute the change in the issues. And what happened sometimes is that there was a different scheduling in the parent and in the current. And if the issue was not found in the parent but was found in the current, then it was reported as a new issue. And for that, we switched to a new, like a different scheduler, which is more deterministic. And finally, some other false positives were related to flow and path insensitivity. So, for example, we have seen instances where a call was guarded by some flag which was only enabled in debug builds. So these were false positives. And we have also seen examples where we would have needed flow sensitivity, where basically the sanitization happened in a way where developers called a particular function to start a block which they considered as sanitized, and then finally they called another function to end this. Just a few words about performance. In general, it's quite hard to measure because in production we have caching, we have multiple checkers, Infer is running in parallel. But in general, the continuous analysis that runs periodically, it takes 33 minutes to compile the entire WhatsApp Android and around 50 minutes to analyze, out of which if you only run reachability is 15 minutes. And on code changes, the total time, including the 2 runs for the parent and the current with all the checkers, but only limited to the change files and their dependencies, is around 30 minutes. So the key takeaway here is that this analysis is fast enough to run multiple times in continuous mode, and it can also provide timely feedback to code changes. And in general, reachability is not the bottleneck. There are much more expensive checkers in Infer. So yeah, thank you. And if you want to learn more about the other kind of code analysis that we do at WhatsApp, then you can check out my website.
Thanks, Ikosh. We have time for a quick question. All right, I had a question over here. So when you mark these methods, or I suppose you asked developers to mark methods as being expensive, the sinks. How much pushback was, well, I wonder, the pushback is perhaps the second question. How much effort did it involve?
So the good thing is that there is a dedicated team for app health. So there is a team who's particularly responsible for the health of WhatsApp Android, and they were quite eager to put in all these annotations, but also having these regular expressions helped a lot to annotate code at a large scale in a concise way. So there was a considerable amount of effort, but yeah, we had help to do that. And we have also seen examples where, for example, the app health team started to put in all these annotations, and then engineers outside of the app health team, they see that oh, we have now these annotations and we can find these kind of bugs. This is super useful. Let me put in some annotations into my own modules. So we have seen these kind of examples, which was very nice to see, because yeah, often in practice it's hard to motivate developers to use annotations and to use specifications, but here they were quite eager about it. I think it's also related to the fact that in the past 2 years there have been some, issues with the app health quality, like more and more crashes. So quality is a top concern nowadays. So even coming from higher above in the company. So
Thanks a lot. Thanks a lot for the presentation. I think maybe I missed something when you mentioned the Kotlin problem towards the end. You said that there is no fixed point computation for the cycle, and I missed this part. Is
yes,
it
so
a soundness limitation that you just decide to have and that's okay, or is it, or did I miss some reason why it was sound?
So that's actually two separate problems. The Kotlin problem is when you have a Java code and you convert it into Kotlin, then basically you had one issue which disappeared, but then you have another issue which appears in a different file with different name, different code. But in theory, it's the same issue. You just move it from one implementation to the other. And Infer is not that smart about figuring this out. But at the moment, we can live with it because usually this doesn't just affect Infer, it also affects all the other static analysis and linters. So when people do these kind of conversions, they usually expect that since it's a new file, they will see issues that are pre-existing. The other thing related to the recursion is again something which at the moment we don't have fixed point computation, which means that with this deterministic scheduler we mitigated the problem in the sense that the issue is either found or not found, but it's at least deterministic. So if we do 2 runs, one on the parent, one on the current, they will agree, and we won't report an issue as if it was new, or we won't report an issue as if it disappeared. However, it is true that we might completely miss issues, but this is something that at the moment we accept.
Okay, thank you. Actually, that brings me to another related question. I know that Meta also has another tool for taint tracking, which is Zoncolan analyzer by Francesco Logozzo. And when you started the presentation, I was very much expecting you would come towards this tool, which, if I understand well, does not have this limitation with fixed point. So did you think or compare the two and try to think about which one would be the most adequate? What are the reasons why you went towards Infer?
The primary choice behind Infer was that here we are mostly interested in tracking control flow and not data flow. And I think Zoncolan is mostly targeting data flow with the taint analysis. And in Infer we already had this checker annotation reachability, which was doing kind of exactly what we wanted. We needed to do a little bit of extensions, but it was more or less fit as is off the shelf, and it was tracking control flow. So, and this checker was actually a couple of years ago developed to solve similar problems in the Facebook Android code base. However, after some time, people started to get somehow less interested in the problem. Maybe they didn't have like a dedicated team responsible for the app health, but I do know that it helped during some conversions there as well, like I think when they were modernizing the feed. But yeah, for us it came out to be very useful as is off the shelf. But I mean, it would probably be useful to take a look at Zoncolan to see if it can do any control flow analysis as well, and then compare.
All right, perhaps we can take the remaining questions offline. Let's thank Ekosh once again.
last keynote speaker is Charles Jiang from Hong Kong University of Science and Technology. He will going to talk about his journey to build a static analyzer for enterprise scale softwares. Please give him a big hand.
Thank you. I'm from Hong Kong University of Science and Technology. I've been working in static analysis for many years. So this is a talk about almost more than 10 years of experience in doing this research, and of course joint work with all my previous and and current PhD students, around 12. So many of them have already graduated and made more money than myself. So outline today is I want to give an overview. So my talk today is very high level. I promise that there are no inference formulas. There's no inference rules. There are no induction formulas. So I'll be mostly talking about an umbrella project that includes many interesting ideas. I want to focus, after the introduction, I'm going to focus on a few key ideas relevant to static analysis, mostly how to do path sensitive data flow analysis. And then I'll talk about a few future directions of this project, okay? So this project name is called Clear Blue. So it happens later, I found out there's another product that has the same name. That if you smile, that means you're still very young and healthy. Okay, no smiles, good. So since it's a keynote speech, so I have to do something provocative. So I like to open with how to save static analysis. So maybe arguably that's my personal view, but I feel that static analysis is sort of somewhat on the decline in the past few years. Last year we published a paper is about buffer overflow detection, just to give you some ideas why I feel that way. Sorry. So last year we published ISTA, we won the paper award. Significant work on buffer overflow detection, right? So buffer overflow, this is where the static bug finding started. We found out that where the earlier paper was published 14 years ago. So that's how few people have worked on this in this area. And static analysis was never sort of a mainstream technology, right? It was never on the center stage. It's always sort of a good to have sort of technology. But is there something wrong with this area, with this field? The answer is, of course, no. So let's look at another piece of static analysis technology, which is called X-ray. Right? If you think about it, X-ray is doing static analysis for real-world objects. Here's the inventor. Almost immediately, he invented X-ray at age of 50 or around my age. He immediately started to get medals from the king, and then he's actually the first Nobel Prize physics winner. All right? So that's how successful static analysis in real life is. Actually, it's very fundamental to many mainstream applications, right? So it's a successful static analysis, a piece of static analysis technology. So I keep wondering that how we can learn from that, right? So the two things that attract me the most is that first, X-ray is very easy to use. In addition for giving a good image of what's inside of you or the objects, it is very easy to use without any intrusive preparation. Right? And also that the output of this technology is just data, it's image. Right? So it doesn't really make any assumption of what your intention is. So would like to, software, of course, nowadays is, I think, is as important as any physical objects, real-world objects, but would also love to have something like X-ray for software, right? And I claim that we don't have it yet. We don't have it. So the input is the software, is software by itself. Right? It's not source code, it's software. It's the software that people use. The output should be the data that describe what the software does. And I claim that that doesn't exist yet. So does that really mean that for static researchers in static analysis, are we really not that smart? Or are we really not working hard enough? The answer is, of course, I can only say for myself, but I work enough, very hard, and I think I'm smart. But I think the reason is because the static analysis is really, really challenging, okay? This is meant to summarize for people who really have no idea what static analysis is about, but we analyze programs, right? So for this very simple piece of program, when we try to analyze, we focus on the variables, right? These represent the data in the computation. So you look at it very quickly. There are 4 variables in the program. But if you really programming, you think you understand programs, you know that some of the variables actually takes input from other variables as part of the function argument passing. So that will actually produce more possibilities for the values. But if we consider where the function is called, the function can be called multiple times. This is what we refer to as context sensitive. We actually have to double the size of the variables that we need to look at. Okay, so it depends on where the location is. The variables will take different values. Then we take paths into consideration, right? The path means all these if-else branches. If we take those into consideration, we double the number of variables again. Okay. So in relating to X-ray, this sort of describes the granularity of the image, right? So of course, the higher granularity that we'll be able to look at, the better quality of the image we can produce for the behavior of the software. So the important takeaway message here is that we work so hard on static, we're so hard on the algorithm, right? We try to speed it up, right? So we have a cubic for pointer analysis, for example. We have subcubic improvement on the analysis. But don't forget that the base n is already exponential, right? So it doesn't matter how fast your algorithm is, the number of variables to consider is exponential. That's just a physical fact to me. So look at this, this piece of software. This is a Linux kernel, and we are able to pretty accurately compute its call graph. Right, so this is a call graph of 381,000 functions. Right? So if you take this into your picture, combined with this story, it's not because we are not smart enough or not working hard enough. It's just because this is a real monster. Right? It's just so hard to be able to. This is so complicated than any of the physical objects. Right? So that's why X-ray can succeed, but we haven't found it yet for software because it is just so complicated. And there are even more bad news. I work with enterprise a lot. So enterprise means that these are the big software that provide sophisticated ongoing services for many people. okay, such as the Linux kernel. So they're not only big, they're also changing, they're also alive. From Linux kernel, every 6 minutes there is a commit. Okay, so so this is very easy to tally. You can just look at the GitHub data. Of course, as how we develop software is getting more mature, any mature manufacturing actually has more integration than development, right? So you actually purchase software from other vendors. You take open source software and then you put them together, right? So this degree of integration is only gonna get bigger and bigger, right? So, which means in your software, the software people really going to experience. There's going to have a lot of what I call dark code, means that the software you have no control of. You don't even know what's inside, right? You purchase them through its compiled form. And also this push of what we call cloud native means that we write these lambdas, right? Lambda programming. We partition our programs into microservices, right? This is how we build for these big scale software. So easy to develop and they're very elastic, right? So, which means that the program that you write as a developer is very small, right? So when you apply your static analyzer, it's going to be very happy. It's going to chew your software for breakfast. But it has nothing to do with the end quality of the whole system, because the whole system is very big and complex. So how to do static analysis in that setting? Of course, also the knowledge we extract from software is more than just finding bugs. We have a lot of other tasks that we need to serve. And often the companies that I work with often require us to solve all of these problems. Otherwise, what's the point of using your tool? So that's really the scary story. Right? So from these observations, here's something that we want to build. I think that sort of behave more like X-ray for real-world objects. Of course, the basic premise is that we need to produce somewhat good quality image. And also, we want to actually produce the image through a non-intrusive imaging. Right? So we don't want to actually interfere with software development cycle too much. Ideally, we would like to scan software from their product form, meaning mostly compiled code by code. And just because of the sheer size of the enterprise software we have no choice. We have to learn from how people deal with big data. We have to use distributed computing, cloud infrastructure to analyze it. And we have to do incremental analysis. Otherwise, it's impossible to handle the scale. And also, the goal of the static analysis is to produce data, is to produce general forms of data. And we're going to let APIs, DSLs, even LLMs to look at it in any way they like. Okay, so this is something that me and my group been trying to build for the past, let's say, 7-8 years. So the answer to that is the Clear Blue project. So here is the architecture of the tool. It's a tool. It's two chain. So what intake to the two chain is basically binary. Okay, so any forms of binary or Java bytecode or the machine binary. So our tool is going to. We're not doing decompilation. We're doing lifting. Right? So we're lifting these binaries into, we choose to use LLVM IR. Right? So we're lifting them into IR. And then on top of that, we do a lot of interesting static analysis, such as call graph building, pointer analysis. Lots of type inference because we're lifting from binaries. So there is a precision loss. So after that, we'll produce some kind of graph representation of the behavior. Basically, it's a PDG. Okay, it's a program dependency graph. On top of that, we have a lot of techniques of finding specific bugs. Okay, so these are the papers we published describing different parts of this tool chain. So if you're interested, you can find more details. So this is just what I just described. So what we try to do is we basically try to build whole program PDG. It's not an easy task. And then we store it to disk. We build indices so that we can look up fast. Then we support analysis on demand. So these are the different I just basically just described. I have more details later on, but these are just the different basic steps of how ClearBlue works. Okay. So the main technical features of ClearBlue is that we basically are good at or focused on doing value flow analysis. Okay, so not the we don't have, for example, a lot of value abstractions. We're handling things like abstract interpretation. We don't focus on that kind of problem. We focus on value flow problems. We're pretty precise, not as of course as ideal as we wish, but we can analyze Linux kernel, for example, 30 million lines of code with 6 layers inlining and full path sensitivity. Okay. We can do asynchronous analysis, means that we are pre-processing these programs and we extract some representation and we store them onto disk. And then we query later. So when you try to find, for example, bugs, you can write queries and extract this data from disk. It's non-intrusive analysis, right? We don't require you to modify any of these your manufacturing process, right? So one painful lesson for any static analysis person is when you try to deploy it in reality, you're going to face with what I call the last mile problem, is that you have to modify how do you extract the symbols, right? So you have to modify the product development cycle of the software company, and which is the last thing they want to do. Okay. So by analyzing binaries directly, we can do it out of a box, so we can support all of the major binary formats, including Java bytecode. So we have some APIs to facilitate very quick definition of value flow queries. Basically, they are just graph traversals. Okay. As a joke, I think you probably hear the joke already, is that everything the PR community is doing is trying to repeat what database people already did. Okay, so well, in our case, it's sort of the same case, right? So this behaves indeed like a database system. So next, I can let's try to be a little bit more technical. So let me talk about some of the essential innovations that we did for inside ClearBlue. So again, this is back almost 10 years ago. So originally, we we published a paper, PLDI'18, called Pinpoint. So it basically summarized the core techniques that we still use today. Okay. So the main idea is that for enterprise scale software, so some people are going to probably hate me for saying that, but we give up on soundness. So for software of that size, soundness is not that useful because it gives you too much information. All right? So for developers, it was just impossible for us to filter out anything that's really valuable. And for software of that size, precision is impossible to achieve. Right? So how do you know the report of your static analysis result is precise? Unless you give it a POC, right? Unless you give it an input and produce the bug. But how can you analyze all the way to the main function? Sometimes you don't even know where the main function is, right? So precision is impossible to achieve in this setting. So what do? Let's produce something. Okay, let's produce something that's more likely to have some value, right? So which means that we want to have the highest possibility of precision, which is path sensitivity, of course, plus context flow, all these sensitivity fields, right? So all these sensitivities, we want to, in particular, bring path sensitivity into the picture, but with a fixed window, right? So with fixed levels of context. Right? So hopefully we can produce some good results in software of that size. And the core idea is not really, I would think that we actually borrowed a lot of good ideas from existing work. So our focus is to try to address path sensitivity, so borrow from famous work Callisto, that we encode path condition as a Boolean variable directly inside the PDG. So using path condition as a variable, later on I'll have some examples. Use path condition as variables allow us to actually pre-filter a lot of obvious contradictions without really calling set, right? So set is another monster. We do perform pointer analysis, but we're going to do it purely local, right? So intra-procedural pointer analysis. And then we borrow ideas from Saturn to explicitly expose the side effect across the function boundaries, okay? Why do we do that? The end result is that those people who are familiar with conventional value flow analysis, that you can imagine FDS, supergraph, but with pointers all resolved, and with path conditions encoded inside, all right? So that we can do one traversal of reachability query, and then we can collect everything into one query, right? We don't have to do a separate path-sensitive point analysis. We can do everything in one traversal, in one query. Of course, there's the ugly side of it. This is the bottom of the slide. That's why it's very ugly. Is that we have to impose very harsh limits on how we do that. All right. So, for example, our inline levels. So the context level we can look at is kept at a number. So usually kept at 6. And since every low stop pairs are gated with path conditions, we have to limit the number of different paths that each low store pair could be matched within a number, typically 10. So this is the sort of the limitation we impose so that the analysis can actually finish. Okay. So just give you some detailed example of what I just said. All right. So given the program on the left, we have some pointer operations. Right? There's a load and there's a store. Okay. So our first step is to transform this program into another program that would directly expose the side effect of input and output. So the input is a pointer P that's being loaded, which means its content is being accessed. So we actually produce what we call auxiliary variable on the input, which is integer x. Since P, the pointer P is also being stored, which means that we have to produce another variable. So the function, the test doesn't return any value, but in this case, it actually returns a value. And we actually explicitly change this function to return the value, to represent the side effect that's coming from the pointer. So in transforming that, then we transform the caller, which is the main function, so that the result is that everything is purely data flow, right? We don't have a two-level pointer here. If we have two-level pointer, there will be a sort of the alias that also flows. But after this transformation on the graph on the right side, there are no pointers. Everything is just a data flow. If the data is actual literal integer or float, it will represent the flow of that. If the data is an address, it will represent the flow of pointer. So, so given this graph, we can do on-demand analysis, right? So we want to query if the malloc can flow into the mem copy in the main. We can just identify the source and sink, and try to compute path-sensitive reachability, right? So another feature is that since we represent this path condition using a Boolean variable, we can just use the Boolean variable to represent the path condition. So in a complex graph, there will be interesting results when we abstract actual path conditions, just use Boolean variables. But this is basically what the core idea is. So with this graph, you can do a CFR reachability if you do top down, or you can do cloning if you do bottom up, right? So it's up to you to how to do your search efficiently, but it's purely on demand. There's no pointers to solve. So so this is great. So we can do pointer flow and data flow in one shot. There's no separate stage for doing pointer analysis. So this actually saves a lot of computation. But we hit another bottleneck is because we tried to do path sensitivity. So as you can see, every query involves set. All right. So set is basically becoming a big bottleneck for performance. In this case, we identify that set formulas actually takes up a lot of space. So the process of finding bug for pinpoint was bottom up. So we compute summaries and we actually inline bottom up. But doing that, we found that there's a lot of path conditions that has to be inlined, has to be concatenated. And this actually hurts scalability a lot. So the observation we made in this paper is that we can actually only store path insensitive information, sort of doing a path insensitive inlining. And once we found an interesting path in the value flow for bug finding, we can actually recover all the path conditions from the IR itself, right? So we just look at the LLVM IR, and then we can just retrieve all these path information. when you look back, it sounds very trivial, but somehow people know it's, at year 21, people recognize it's a good idea. Another observation we make is that once we know the program structure, we can actually save a lot of effort in encoding path conditions. For example, when we're encoding path condition for function foo, we have to consider how these variables flow inside function bar and come out, right? So, so usually we will encode everything with a big formula. A quick look into the function bar is that we found that the input and output has no other path conditions. It's just a linear relationship, right? So there's no use to encode all these linear relationships. So it's equivalent just to ignore whatever's inside and then encode the condition directly without, it would be, so in terms of set, it's the same result, right? It doesn't really affect anything. So by leveraging the program structure, we can actually speed up set a lot. So this is what we did, follow-up work in PLDI'25. The result is, of course, the big saving is on the memory reduction, so we save a lot in storing these path conditions. The memory reduction is quite considerable. There's also follow-up work on that, which is ongoing. So this is unpublished, but I'm happy to talk about it. Is that the earlier work we save space, now we try to save time, right? So how do we save time? Is that in the old IFDS problem solving, basically there are two approaches, right? So one is the CFL reachability, where you from top to down, and then the downside is every time your query changes, your summary has to be recomputed. Right? So although you only traverse part of the graph that's relevant. The clone-based solution is interesting. It saves a lot of effort in reusing some of the clones. And if you have multiple source and sink, it can probably also address that as well, because you're doing inlining, you are actually probably looking at, on the way, you can do more discoveries of other source and sinks. But it requires a lot more memory, right, compared to the top-down approach. So we like to combine both. So we like to do reachability. We like to only traverse part of the space that's relevant, but we don't want to actually clone the summaries. But we do clone the summaries, but let's do it in a different way, right? So the difference is we can clone the summaries and we store them on the disk, okay? But we don't just naively clone these summaries. We pre-compute reachability, right? So using CFL grammar and set. So we pre-process these summaries. It's just for value flow purposes, okay? And we store them on the disk. The perceived performance is that when the users are actually using the tool, the perceived performance can be greatly speed up by loading these summaries from a disk instead of actually computing them, right? So we can only look at the sort of the additional lag when we know where the source and sinks are. We just look at the additional lag in their intra-procedural inside their function, and then the rest of the paths can be actually looked up by from a table, right? What table? This table. So this is a quick example. So these different colors represent the entry point and the exit points of these function summaries that we built. So the summaries are similar to the ones that I just talked about before. Then from that, we compute sort of the the value flow paths, right? So for example, there's an entry point to a function. Let's compute all possible paths that can come back, okay? Of course, possible means that they have to set, and they have to have CFL grammar, right? So the sentence is valid on the CFL grammar, and the condition is a set. Okay, so we can pre-compute all these different paths, shortcuts, and just list them on a table, store them on the disk. Okay, and then after a physical query comes, var 1 to var 5, we only need to build up the local connection to the entry points and the exit points of these summaries. And the rest of the paths just can be looked up, right, by the keys to the table. Okay, so basically it's a reachability search for the query and a set check. Of course, this is still somewhat a naive approach. We're still working on making it even more efficient. But as a prototype, it also shows the sort of the benefits, sort of the speeding up. So the overall process is not necessarily shorter because we have to spend a lot of time building these indices. But I think this is the sort of the offline time. As user using the tool, the speed up is dramatic, right? So sometimes it's 200, 300 times faster compared to pinpoint, right? Compared to pinpoint. So this is an interesting, also interesting direction that we're heading. So the last part is, of course, we have a lot of other work that deals with other parts, but I think the most interesting ideas are these ideas. But how can I I must do you a very good service by talking about LLM, right? Nobody talk about LLM today. I feel like I have to do you a good service by talking about LLM. So how does static analysis, or the conventional notion of a static analysis, interplays with LLM? Okay, so our experience has been that it's pretty good in certain specialized tasks, which we call it boundary problems. So what are the boundary problems? Boundary problems are the parts of the software that's missing. So there are many different scenarios why they're missing. Of course, they're missing, right? So that's one scenario. The second one is that they're in binary. So recovering from binary is a challenge by itself. Some binaries are heavily obfuscated. Okay, I have also seen other applications that the binaries are dynamically downloaded, so it's just impossible to have. But then there are also limits of static analysis, as well known. For example, the understanding of shapes in the big scale, right? In the big scale, plus loops, right? I.e. Recursion. So these things are very hard to analyze. And also because of the size, right? So it's just impossible to be precise. So these are the things that are impossible for static analysis to address, but the users, they don't care, right? So for them, this is their software. They don't care how you do it, but please give me some useful results. I'd like to quickly share three case studies that we use LLM. The first one is alias through containers. That's when shape analysis is impossible for enterprise software. And also, we have some experience in analyzing operating systems. The final case study is LLM versus static analysis. Right? So hopefully they're interesting. So the first case study is data flow through containers. Right? So containers, collections, abstract data structures. So these are things that are very hard for static analysis to get accurate. For example, we can store something into a hash map using a key, and then we can use the same key to retrieve it, right? When we do that, we know that these two results are the same. And then with that, we can establish a data flow, and then we can proceed analyze a lot of interesting bugs. Otherwise, it's broken, right? Modern software uses this a lot, so a lot of the paths are broken, which is not good. But is that so hard to analyze for a human? So our intuition is that for certain kind of API pairs that come with the containers, as a human, we can actually quite easy to deduce that certain things are aliases, right? So for example, push and pop, right? So when you push something and then you pop, you know that very likely, right? When you push something, you pop immediately. That's a trivial case, but you know that these two things are obvious aliases. Otherwise, that would be very difficult for static analysis to give you that conclusion. But it's very easy for human to deduce that. So what do? We first look at the type signatures. We read the documentation, right? We read the documentation. We read the type signatures, and we read the document. We actually read the sentences, and it's not hard for a human software developer to reach that conclusion. So this is the intuition we had. So these are the two observations. Just quickly skip them. So if we combine them, we ask LLM, and we combine with these type constraints. We combine them together. So let's see, we can make some right conclusions. So this is called so this project is called DA'25. It's in the last year FSC. So the result is that it's quite interesting. Right? So these are the things that static analysis, which is no oracle to compare to other than from a sort of subjective judgment, right? The precision and recall are reasonably good, right? So around 80%. Most importantly, we can find additional flows, right? Compared to using the traditional static analysis tools. We can find additional flows. I did another interesting experiment following that. This is not part of the paper, but I told my students that, so this experiment was done in 2023, so let's see if we can do better, right? So we have more powerful AI models now. So let's repeat the experiment, right? Using all these up-to-date, well, maybe not up-to-date anymore, but newer models. And let's repeat the experiment to see what happens, all right? So this, maybe you can ignore the numbers on top, but these are the summary of the accuracies down here, okay? So one interesting discovery is that in this case, DeepSeek is pretty good, but on average, they're pretty much on par, okay? Means that, so for this kind of knowledge, right, so it summarizes the knowledge. Maybe the models, the old models, are already good enough, right? So about knowing something, maybe reasoning model does not really do anything dramatically better than the non-reasoning models. Okay. So this is an interesting experiment we did. This is another experiment in detecting bugs in kernel. So the story is that we have, so traditionally when we detect deadlocks, right, so we detect the cycles in nested locking, right? So when we follow the control flow, assuming perfect knowledge, even if a thread does not really acquire locks nested in successive manner, meaning nesting, you could still have nesting with interrupts. Okay, so when a thread acquires a lock, an interrupt can come and grab another one, and then you're gonna have deadlock. All right. So, of course, the first job in doing this is to find out where are the interrupts are. So when we process the flow, we have to find out where the interrupts are. What functions represent interrupt handlers? So that's the sort of the task, first task. So naively, we would feed the name of the function to LLM and ask if this is an interrupt handler or not. All right. It turns out that this is a very terrible choice. It has roughly no idea how to answer the question. Right? So 56% accuracy. It turns out that if we can combine static analysis a little bit with LLM, we can dramatically improve this capability. Okay, so the static analysis is very simple. We simply detect sort of a pattern. So in kernel, interrupt handlers are often registered as a field for some kind of struct that describe a device. So this pattern is really easy to detect, and we find these functions, address taken functions that are being actually passed into these structs. Okay, so this is some very easy static analysis that we can do. After that, we're going to tell LM, this is what we found, and please look at this particular function. Okay, so sorry. Yeah, in this example, please look at this particular function to tell me if it's a interrupt handler. And but doing that, we can actually have a lot better performance. Okay, so we can reduce false positives from the naive version of LLM. Okay. We can reduce a lot of false positives. We can find additional bugs. So this is a very interesting interplay of LLM with the static analyzer. Whereas the previous case was just relying on LLM to find knowledge that static analysis is unable to find. The next little case is about fighting LLM versus Clearblue. So this is what I asked another student try to detect memory wrappers, right? So this is very important for taint analysis, or for value flow analysis, the earlier talk, right? So you have to detect if something is coming out of memory allocation, maybe you need to sanitize on it. Okay, so it's important to detect these memory wrappers, and trust me, memory wrappers are very hard to detect because you just have no idea how people wrap up the memory, the preliminary functions, and how people wrap them up. So the experiments is that we identify, so this is another benchmark, identify 800 kernel functions, 200 wrappers, 200 free wrappers, and 400 non-memory management wrappers. So this is a benchmark, not from us. So we're going to use it to test, to compare the capability of Clearblue versus LM. Okay, so this is the experiment. So we implemented an algorithm for dedicating to find memory wrappers on Clear Blue, and we compare that to LLM. So we see who is doing better. Some details about how we do it. So we picked some of the newer models as well. Right. Some details about the prompts that we use. The result is very interesting. So we first prepared the benchmark about 20,000 candidates. So these are the random candidates. But they, so there's no oracle for Linux kernel, right? So, but we try our best to filter out 20,000 wrappers. And inside the 20,000, we're going to see how many of the technique, how many of the wrappers, true wrappers, can be picked out, because we have some oracles, some known facts. So that's the way that we compare. So this is how each model, how many wrappers that each model picked up. Okay, so for example, out of these are there's a sort of man-made benchmark, but each model can pick up a small subset of these wrappers. In terms of quality, we just look at how many. So among the wrappers that picked up, how many of them are in the oracles that we know they are accurate? In this oracle, there's 800 calls. Okay, so that's what we do. So the observation we make here is, surprisingly, LLM model in this task outperforms Clear Blue by a very large margin. Okay, so this is what we. In terms of recall, they are roughly equal. Okay. So this is for the right. This is for the allocation wrappers. This is for the free wrappers. This is for the free wrappers. So the LLM models are also on par with the static analysis. So in this way, actually everything is roughly equally good. Okay. So here are some case studies why for some false positives and negatives for this comparison, right? So. So this is a case where static analysis failed to find because the call chain is too long, right? So this API is called alloc pages, but involves a very deep call chain. So the Clear Blue is not able to figure out the data flow. Another case where LLM fails is that the name of the function doesn't have a little connection with idea of memory allocation. It's called on register. But basically, on register, it means that it's going to clean up the memory. In this case, Clear Blue is able to figure out the data flow because it's pretty shallow, but LLM cannot. Okay, which is, I think it's predictable. I guess that's all that I want to share in the work that we did. Some takeaways is that static analysis is still a very big challenge. I think not because it's not important, but maybe we have to try to look at some interesting new directions. So there's a need to bring static analysis to product perspective of software. Right? So instead of traditionally it's R&D, it's developer oriented, but maybe we can also look at more on the product perspective. And LLM is surprisingly effective in solving all these specialized occasions. I have no general conclusion, but at least it's better than not having it in many of these cases, right? There are some future directions. The first direction is to open source it. The reason why we didn't open source is to embarrass the open source. I often found functions of 5,000 lines. But students have very little motivation in actually having a better modularity. And we'll continue with data-driven static analysis. I think static analysis is also good on having high-level abstractions. A friend in Purdue is doing static analysis on network protocol interactions. This is having great success. In that, you can don't have the scale problem. And we're also experimenting with agentic approaches to work with LM to actually produce POCs for the bugs that we find. Okay, so I think that's a more valuable output for the users. I think that's it. Thank you so much. We have a semi-working website that tells more information, but don't trust too much on that.
We have a couple of minutes for questions. So, any question?
Thank you for your good, very good presentation. I have one question about the memory wrapper identification and how it can be used in scenarios. How can memory wrapper identification be used?
The wrappers they act like a disguise of something very important. They look like regular functions, but they're actually very important compared to other functions. So memory wrappers are memory allocators, for example. The variables returned from that is probably worth attention. You might want to sanitize it, or you want to actually, do buffer overflow checks on these targets, right? So otherwise, you're going to do buffer overflow on any of these variables. But if you know that it comes from a wrapper, then it probably can focus your analysis on that. And also sinks, right? So freeze. If some memory is free, then you probably need to look for, double free or use after free problems.
Also, in a sense that we may focus more on such.
Yeah. We want to know that certain variables represent important information.
Thank you. Thank you for your clarification.
Any other questions? So let me ask one question.
So this is maybe a super specific question, but you had this example about trying to detect the deadlocks with the interrupts, right?
Yeah.
So I was wondering what actually the problem was in the example that you showed, because it seemed that there would only be a deadlock if the interrupt in turn was interrupted again.
Yeah, it would be another thread. I didn't show the big picture, but there will be another thread and another interrupt. So they will be forming. So you log 01 and then log 02, the other one log 02, and the interrupt log 01. So
two interrupts.
When the interrupt comes, when the interrupt comes, that the thread has a lower priority, right? So the thread would be suspended, right?
Right,
so
but you would need two interrupts to interrupt each other for the thing to be a problem, or not? Because your handler did the unlock, your interrupt handler, and I guess then then you have another interrupt. Okay.
That could actually form the So if you look, so the problem is look at the program flow. There are no nested locking, but when you consider interrupt, there will be nested locking. So that's that's the problem. But that's not the.
Thank you.
Yeah.
So time's up. So let's thank the speaker again.
Thank you.
So next talk will be next speaker. Okay. So we have two paper talks. The first talk will be offline. The second talk will be online. The next talk will be about towards bit level dominance preserving quantization of neural classifier by Dora.
Yeah. So hello everyone, and thank you so much for attending my talk. So I am Dora, and I'm from ENAC. It's the French National School of Civil Aviation. And today I will be presenting our paper towards bit level dominance, preserving quantization of neural classifiers. So this work is in collaboration with Mathieu Martel from University of Perpignan in France. So, as we all know, GNNs nowadays are massively over-parameterized. So, for example, if you take models like GPT-3 with more than 1,075 billions of parameters, we have also models like Llama 2 with more than 70 billions of parameters. So these huge numbers of parameters make such models hard to deploy on real-world embedded systems, especially that these systems have some limited resources. So here we talk about resources in energy, in memory, and bandwidth, etc. So let's take a concrete example of the model Llama 2. So the Llama 2 with 70 billions of parameters have been trained on 6,000 NVIDIA GPUs running non-stop for 12 days to make the computations. So this takes 1.7 million GPU hours to fine-tune these models. And the output of this model was compressed, and the final file is of 140 gigabytes. So why I'm giving these numbers and giving this discussion is that to show that it's true that such models are huge and are complex, but sometimes we do not all need all this complexity, and this is why there are some models or some new techniques for doing reduction and optimization. So there is a need to do some optimization, but the key question is what can be reduced? So many optimization techniques are available and are in the state of the art. For instance, we can reduce the number of weights of these models. Techniques like pruning and like knowledge distillations are available for this. The second kind of reduction technique, and which interests us the most in this talk, is the quantization. So when you take quantization, you want to reduce the precision of neural networks. So how low can we go? So when we reduce the precision, either we reduce the floating point precision for which the neural network has been trained. For example, we move to 16 bits or 32 bits, so for reasons for speed and scale. The second one is to do some mixed precision, which means that some neurons or some precision will be in 16 bits, the other one 32 bits. So we merge several types of precisions in order to give a good trade-off between performance and accuracy. There is also another type of quantization, is to change the arithmetic, is to convert from floating point arithmetic and to go to fixed point arithmetic, which is based on integers. So in this work, we are only interested in doing quantizations, but by keeping the floating point arithmetic for the quantized neural networks. But once we have done the quantization, what should we quantize when we do such quantization? So generally, or in the literature, the state-of-the-art models that do the quantizations are doing quantization based on error guarantee that they give on the output model. So what they do, they take the floating point neural network and they go to, and they give on the output an error guarantee, for example, that the error bound between the original floating point neural network and the quantized one must be less than a small error, which is here epsilon. So tools like Aster and previous tool of ours like Poppins do this. They synthesize fixed point codes for neural networks, but based on such guarantee. So this is very good. So our outputs match original network. However, this method does not suffice, or it's not enough for doing quantization. Why? Because it's true we give guarantee on error bounds, but it's not a property or functional property that determines that the quantized neural networks behaves correctly like the original one. So, and in this talk, what we are interested in is in quantizing neural networks, but giving guarantee on a more important functional property, which is dominance. So, which is dominance in the case of neural classifiers is keeping the order of output unchanged for the quantized neural networks. For instance, we have two classes, class A and class B. So the output of class A, for example, the score of the output of class A is higher than the output score of class B. Then after quantization, with our method, we want to, in the quantized network, this score is unchanged, which means that class A is always dominant than class B. So how to do that? So this is what I will explain in this talk. So the goal is to preserve the dominance quantization of neural classifiers. So how we proceed is by determining the minimum precision required for quantization to ensure the preservation of dominance. We will perform only post-training quantization and with uniform precision. Uniform precision is mean that we all have only, for example, 16 bits or 32 bits. We will not have mixed precision at this level of work. And we will compute by this post-training quantization the minimum number of Montesa bits. So the Montesa bits are either significant of the floating point numbers. And we will compute such precision independently of the IEEE 754 formats, which means that we will give the new precision at bit level. For example, 9, 8, 18, etc. So from now, we will introduce two types of precision. The original precision, PO, we denote it, so which is the original full precision of our, for which the neural network has been trained. And what we want to compute is PR for precision reduced, which is the unknown and we want to compute by our method. So of course, the two precision are in F, and F is the set of all floating point numbers. So let's go a little bit inside the method. So how to do the dominance of neural networks. So simply we consider a neural network. The input of our neural network are x, so the vector x here with n, with size of n, and the vector x is in the original precision. We have a matrix of weight w, so the matrix of weight of size m times n, and we have y, so y is the output of our neural networks, which is the size of our output are m, and the neural network is doing just multiplication, so the output y is a multiplication of x and y. So we say that a class E is dominant for some E if we have two classes, for example, E and G, so the output of the class y is greater or equal than the output or the score of the output of class G. So this is the basic definition of the dominance. So in this work, I'm just going to talk about dense layers. I will not present activation functions, and I will focus only on single-layered, fully connected neural networks. So as maybe you know that when we perform floating point computations, so there are errors that can occur or are introduced in each operation. So these errors are captured by what we call epsilon machine. In other words, epsilon machine is the gap between 1 and the next larger floating point number in a finite precision. So why I present an epsilon machine? Because in the context of quantization of a neural network, so when we quantize or reduce precision, we will introduce errors in the neurons. So these errors that are introduced, we need to bound them with so we bound such errors, and we will use the epsilon machine to determine how much precision that we can afford to lose without changing the predicted class. So, and then the epsilon machine is equal to 2 to the power minus p. So here, when I don't say p original or p reduced, so I'm talking with on both precisions. So following the standard model for floating point arithmetic. So here I take the input, the output, and the matrix of weights in original precision. In the quantized neural networks, we have x hat, y hat, and w hat, which are our new input, output, and matrix of weights in precision, or in PR, which is the reduced precision. So equation 3, 4, and 5 are so when we are the new, or the definition of x hat, which is x times 1 plus certain error, y, which is the matrix of weights, which is the matrix in floating point original precision times 1 plus certain error, etc., and y, which is the result of the dot product. So if we follow such these equations, 2, 3, 4, and 5, so we say that the dominance is preserved if we have a quantized neural networks, if the original so the original output of class I is greater or equal than the class G, then in the quantized neural networks we will correct this inequality. So for that, we will apply in this work the theorem of Ramp's error bound on dot product. So what tells? This theorem was published in the error estimation of floating point summation and dot product journal paper in 2012. So Ramp said that if we take n-dimensional vectors x and y in a precision, and we have the new floating point or the new x hat and y hat in a reduced precision, then the error bound of the dot product can be bounded by such quantity. So, and we will use such theorem in order to find the reduced precision that you want to compute on our quantized neural network. So let's do it. So we will follow the Ramp's logic. So we will take our classes, so the output are our classes, so class E and G, and we have YE, which is the dot product WE XK, and we have the other class, the output G. We will take the same, but in the absolute value, and we'll propose or define this new proposition to preserve the dominance, or the condition to preserve the dominance. So following Ramp, so the dominance of class is preserved if our epsilon machine, which is the error bound of the quantization of our neural network, is less than equal than this quantity. So the full proof of this proposition was provided in the paper, and this orange inequality guarantees that after the quantization that we did with our methods, the predicted dominant class remains unchanged. So, as our goal is to minimize the precision PR or P-reduced while preserving the dominant class, we found that we are in face of a nonlinear optimization problem. So this is this huge inequality is the problem that you want to minimize. So what we have as known or unknown parameters. So what we know is n, which is the input vector dimension. We know the weights of our neurons. We have also xk, which are the elements of the input vector belonging to range between 0 and 1. So all these are known before before solving our problem. And what is unknown is the PR, or the reduction precision, that you want to compute by our methods, and which is given by some epsilon machine u is equal to 2 to the power minus PR. So to solve this problem, so we in face of a nonlinear constraint to find the smallest PR that guarantee the dominance. So to solve this, so we need to find, to maximize the epsilon machine in order to find the smallest PR possible for which the quantization guarantees the dominance of our classifiers. For that, we will use the optimization method known for the large-scale problems, which is the trust region constraint algorithm. So, which is based on an anterior point algorithm to solve large-scale nonlinear programming. So we have tested only this optimization technique. We do not test another solver, maybe in future work. So after solving this equation, so we move to the experimental results. So what we have in the experimental setup is the datasets and networks. So we take the MNIST dataset for handwritten digits, the diabetes for the medical future, the CIFAR-10, which is dataset for RGB images, the cards, which is a dataset for playing cards, the rice for rice varieties and weights, a dataset for recyclable waste images. And here we show the input shape of the dense layer that you want to quantize. So we quantize only the dense layers as we said, and only single layer per neural network for now. So what we need to take in consideration is that all inputs for our models are normalized between 0 and 1, and that the quantization is applied to only the less dense layer, but except for diabetes and weights, which is the penultimate layer, because the last layer is used to calculate or to compute the score. So let's move to the first results. So in this table, what you want to do is to compute the reduced precision PR, and also to show the saved memory that we obtain when doing this quantization. So initially, all our neural networks have been trained in original precision, which is the single precision with 23 bits of mantissa. We take here, we display all our networks, the layer shape of the dense layer. So what we can see is that when we solve our optimization problem, we found that the reduced precision ranges between 9 and 15 for our neural networks, starting with initially with 23 bits. And we have a saving memories falling between 34.7 to more than 60%. So for instance, if I take the MNIST example, so for the MNIST example, so we found that the reduced precision is equal to 9 bits. So, and we can save more than 60% of memory, and with only precision of 9 bits, we keep the dominance, and we cannot violate the dominance of our neural network. So the second experiment investigates the scalability of the method. So here what you want to take is the case of the MNIST dataset, and we will vary the classes. So we'll take, for example, a class 3 and class 5, and also we will vary the image sizes going to 5 times 5 to 28 times 28 images. So what we have here on your left-hand side is the plot of the reduced precision versus the input size. So in the x-axis, here we have the input size of our MNIST model, and in the y-axis, we have the reduced precision PR computed by our method. And the green plot is for the class m equal to 3, and here for the output equal to 5, the blue one. So what we can see or observe in this plot is that we have imported gain in a reduced precision. For example, here for 10 by 10 image input size, we have 6 bits of precision reduced, etc. And also in time of execution time, on your right-hand side, we found that our method for all or across all networks is fast. So if we can find the new precision needed for the quantization in only a few minutes. So let us now discuss a little bit limitations and what we need to do in future work. So as you have said, our work is limited to only dense layers, and for now we don't address the composition of multiple layers, neither for activation functions. So what are the directions that we want to take to address the most common layer types in your classifiers? So for activation functions, so most activation functions, the ReLU, the sigmoid, etc., are monotone. So we said that perhaps if we do not change, so such activation functions do not change the dominance, and they can be ignored during the quantization process. Concerning the monotonic layers like max pool, min pool, upsampling layers, etc., also they can be left as they are in the quantized network. For the convolutional layers, so the convolutional layer, it performs a sequence of operation of this form. So generally, this form, we have a sequence of multiplications and additions. And we believe that they can be performed in the same way like we did in dense layers. And I finish with the multi-layer networks. So when we have multi-layer networks, this is the real problem because it's a composition of the composition of monotone functions is monotone, and this should help in solving the problem. But for now, we didn't proceed to do the composition of such multi-layer networks. So the take-home messages. So I presented a novel quantization method that preserves dominant class for classifiers. Our method does not rely on score approximations, but it ensures the predicted class remains unchanged. We are based on a theorem of ramp in order to bound the errors to formulate a nonlinear optimization problems. And the first experiments confirm that our method is practical for the data sets used. So perspectives, we want, as I said, to extend to more general neural networks. Why not to combine with other optimization techniques like pruning and knowledge distillations, and to explore other alternative solvers to and relax constraints for speed. So that's it. Thank you for your attention.
Yeah, because of this time limit, so we should have discussion offline, a Q&A session offline. So thank you.
Thank you.
The last talk will be remote talk. So optimizing time migration for LLM-based C-Trust translation by Qing Xiao.
This talk will talk about first using LLM in code translation, that is, translating code bases from one source programming language to another target programming language, and then the type migration problem, that is a key challenge in LLM-based translation to ensure correct variable types at the declaration stage. We'll introduce an optimized type migration framework to address this problem and also our results of the experiments. LLMs have transformed code translation from traditional rule-based approaches to a more automated and data-driven way. There are now several frameworks and benchmarks such as COST, CodeTrans that have proved LLM can produce translations that are both syntactically and semantically correct on function and file-level code translation. However, none of existing work achieved a fully automated translation of repositories due to incomplete compilations. This is understandable as repositories are significantly larger in scale compared to individual functions or files. They often involve cross-file references, which are difficult to capture when the entire code base cannot fit in the model's context window. And we have to segment the code, which leads to memory loss. We focus on translating C to Rust in our work because Rust offers strong guarantees that can address some of the memory safety issues in C code bases. Rust eliminates buffer overflows, use after-free errors by its strict ownership and borrowing system. So this challenge is more pronounced in C to Rust translation because C language heavily relies on header files to manage global variables across multiple files. Since there are no existing C to Rust repository-level translation benchmark, we conducted a manual translation with the assistance of an LLM to better understand the challenges that are hidden in fully automated LLM-based repository translation. We selected the gzip package, which is originally written in C, and manually translated it into Rust. The resulting Rust implementation now supports both compression and decompression. We also translate the original test suite from C package to evaluate correctness. The Rust version successfully passed 64 out of 69 tests. The remaining failures were primarily due to differences in underlying libraries or systems calls or logic errors in the translation of internal functions. And we also identified about multiple mutable references. As illustrated in the diagram, Rust discourages global variables to ensure memory and concurrency safety. Global variables and functions in C are translated into struct fields and methods in Rust. Consider the following C code snippet, where functions pass global variables among themselves. If directly translating from LLM, these global variables become struct field, and the corresponding function calls lead to multiple parts of self being borrowed simultaneously. This is because for methods in Rust, the first parameter is conventionally self, referencing the struct instance on which the method is called. And if a C function originally takes global variables as parameters, a direct translation might produce signatures including self and self.x in Rust. Because self.x is part of self, Rust's borrowing rules interpret this as multiple mutable references to the same underlying data within a single call. It is also hard for LLM to detect and fix it because in practice self don't appear before self.x. To address the problem, we employ data flow graphs to track how data propagates between operations and functions, including variables definitions, assignments, and usages. Hopefully, by examining how a variable is used in subsequent code, LLM can avoid passing multiple parts of self to a method. If there is indeed a struct field that is passed to a method, we ask the LLM to pass a enumerator instead, and the enumerator functions as an indicator to tell which parts of self are used later in the function. This diagram shows the correct translation with enumerators. The global variable x and y in C are translated to fields x and y in a struct to meet the ownership requirements in Rust. Then, in a method which modifies x and y, instead of passing self.x and self.y directly, we pass two enum indicators, so the function can tell which part of self to modify without the risk of borrowing self multiple times. And compared to redesign the code or set auxiliary functions, using enum indicators actually preserves most readability and functionality. Here is another complexity in type migration. In C, pointers can be incremented or decremented to directly access or manipulate memory addresses. By contrast, Rust's VAC only allows element access through indexing and does not support pointer arithmetic. Consequently, pointers from C cannot be naively translated into Rust's box, reference, VAC, or slice types. LLM-based translations often fail to make this distinction because C uses the same declaration syntax for both scalar and array pointers. Let's take a look at each type of the pointers, and we can see that even with the exact same declaration, we can assign a value dynamically malloc memory or use it for indexing. But in Rust, each variable needs to be initialized at the declaration stage. So if the context window of a LLM can only capture the declaration of a pointer, it cannot tell what Rust type to map to, and normally it is translated to a scalar pointer and creates an index out of range problem. This complexity is detected during our manual translation where the LLM misinterpreted the type of a linked list pointer. It recognized struct node next as pointing to a single node, overlooking the fact that the same pointer can point to an array of nodes. The diagram here vividly illustrates the issue. For a singly linked list and a multi-linked list, the C-struct node is exactly the same at the declaration stage. But for Rust, the pointer next needs to tell whether pointing to an array or a single node. If not, this creates a type mismatch problem in the future. And the correct translation is so close to the wrong one that prompting LLM to fix this problem is not gonna work either. To address this problem, we also apply data flow graphs, as it is a compacted version of code that tells the future usage of a variable and saves in token limit. The diagram describes our strategy for distinguishing between scalar pointers, array pointers, and pointer arithmetic. After using Clan's static analysis tool to create a data flow graph outlining key pointer operations such as memory allocation or pointer arithmetic, we feed the pointer declaration and its data flow graphs to the LLM, which decides among a box of slice, reference, VAC, or boxes, or index. If it's an unallocated array pointer, we use VAC or box of slice. If it's a pointer to array elements, we use index type that stores the pointer's initial position and handles pointer arithmetic. And if it's other pointers, it will be translated to default box or reference. Our approach targets repository-level translation, where translation quality is ideally measured by the number of passed tests after compilation. However, like all existing methods, ours too struggles to produce compilable code, and compilation error counts does not reliably reflect translation quality. We therefore manually verify translation accuracy by comparing variable types against those in our fully manually translated and compilable code. We translated 151 global variables from 12 C files in the gzip C package, as well as 76 local variables from 8 functions in flat C file. For our experiment, we used ChatGPT-o1 as the language model. The prompt template is in the right diagram. So for global variables, we first ask LLM to create a state struct, and then we ask LLM to create enum indicators for all the variables that have been used as function parameters in its corresponding data flow graph. And for pointer variables, we ask the LLM to translate the function header and local variable definitions within the function. If the data flow graph shows that there are malloc or kloc operations in the data flow graph, we ask the LLM to translate it to a vec or a box of slice. If the data flow graph indicates that there are array indexing or pointer arithmetic in its corresponding data flow graph, we ask the LLM to translate to index type. And if else, it will be translated into a scalar pointer. As instructed in our prompts, for certain global variables passed as parameters to functions or stored in other structs, our methods create enum indicators at the declaration stage. Among all 151 global variables, our approach introduced 14 enum indicators, and this highlights the necessity of these indicators to prevent multiple mutable borrowing. By contrast, the baseline approach lacked the data flow information required to trigger enum generation, and they introduced no new enum values. The blue color indicates global variables, and for baseline it remained 28 of them as static variables, that is, immutable. And the orange is the struct fields, which ensures safe memory management and satisfies Rust's lifetime requirements. The gray ones are enum indicators, that is, to help prevent multiple borrowing problem. We selected the inflatc file for pointer type migration experiment because it is largely self-contained. It defines its own tree node structure and avoids calls to external C files. The upper diagram illustrates the distribution of local variables in inflatc file, which indicates the importance of correctly mapping pointers. Our approach processes each function by first build the data flow graph for all variables in one function. Then the resulting data flow graphs, together with the prompt templates, form the input to the LLM. The baseline method translates the variables without data flow information. And as shown in the lower diagram, our approach successfully identified the correct pointer types and only got 2 wrong. And the baseline failed to distinguish all of the pointers that are not scalar ones, and they resorted to referencing counting cells. This actually suggests that the LLM is cautious about using raw pointers in Rust, and they attempt to work around this by defaulting to referencing counted types. But reference counting is insufficient in this context. It does not guarantee exclusive mutable access, and they fail to properly suggest pointer arithmetic, and they are often required in C code. To conclude, our work identified key gaps in C2 Rust type migration. We propose a data flow approach using enums to eliminate mutable multiple borrowing errors and to select appropriate Rust types for C pointers. One fundamental issue here is that many concepts in C and Rust do not have direct one-to-one mapping. When the target programming language like Rust lacks a direct equivalent for a certain C feature, LLM needs to develop a workaround. However, these workarounds are non-trivial for LLMs to generate and often risk violating the safety or design principles of the Rust language. Other than type issues, we also found numerous other low-level incompatibilities from C to Rust in our manual translation. Like, Rust does not support negative indexing, and they don't support I++ or -i kind of incremental or decremental operators. So more future work should be developed to generate workarounds for incompatible C and Rust features. And also more future work should focus on evaluate translation quality. It would be hard since most translation framework now cannot produce compilable code. And that is all for the paper. Thank you for listening.
So So unfortunately, there's no Q&A session. So if you have any question, please use this Discord channel. Okay, thank you. So can you? So let's have a closing session. Okay, so thanks for coming to this workshop. So we would like to first, Luca and I, we are co-chairing this workshop, and we would like to appreciate all the hard work by our PC committees. So if you are here, so could you stand up? And okay, let's thanks. Thank you. Without their effort, yeah, it cannot be done properly. Thank you again. And we have a Best Presentation Award. So following the tradition, following the convention, for the Best Presentation Award, we give a gift following the name. As the name indicates, we're going to give a soap. Okay, especially for it's very very intuitive. So especially the soap resembling the traditional clothing of Korean king and queen. This one. So we have. We have this gift. Okay. So the presentation award will go to. Okay, ACOS. ACOS. Okay. Okay, thank you. Thank you. Yeah. And that's it. Hope to see you next year. Okay, enjoy.